Good afternoon. Happy Sunday. Hope everybody's doing well. It's a beautiful day today here in Kansas City, so I've got a little bit more natural light in here because it's not really that hot. So, yeah, it's pretty good day. We're going to do some more HanoiDB today. Last time we got the single step merge thing done, as well as if I recall correctly, we touched on some things in the writer, in the nursery, and we figured out how to iterate over all the keys in a database, or rather, yeah, in a single tree. Um, so yeah, that was good. We kind of needed that so that we could go into the process of merging with the right tools. And today, what I hope to get to is we're going to work on building up the structure of the levels so that we can create that merge process and get to writing the A and the B file into the X file, which gets promoted to the next level. And we want to get to the point where we can go use that calculation that the Erlang version used to determine how many keys to merge at each level of the tree, and like push that down through all the levels in a single go. Now there are some. I think that what we'll do, for simplicity's sake, we will do this single threaded. So we'll do this as, if you hit a write that just so happens to get unlucky enough to trigger the incremental merge, then the return from your write is going to be waiting. I think that will be good enough to demonstrate the sort of like incremental cost of merging. But further down the road, we might want to make those merges happen on separate threads, as they essentially do. They're lightweight processes in the Erlang version. They essentially happen on separate processes. But it won't be an async thing. We don't, file system stuff isn't really worth doing async in a lot of cases. And in fact, the APIs for file system stuff in Rust standard library is not async. You have to pull in Tokyo, and then I think it's even sort of faking it, which is interesting. So we won't be building an async API there. It's going to be sync regardless, but we can probably do something for now where it's just single threaded. We do a small amount of work as we hit the threshold for triggering it, that causes that one write that happens to trigger it to potentially incur that cost. But we're not. We do have back pressure. That is, like, I probably said it enough times in previous sessions, but like that is a big point of HanoiDB, is that you don't disconnect the source of saturation, potential saturation in your system, from the thing consuming it. Whereas like when we were at Basho, when we were using LevelDB, one of the big problems was that we had to have separate threads doing merges between levels, and making sure that those didn't get overloaded was a big problem, and you could get big backups. I mean backup as in like a car jam, a traffic jam. Not as in you copied this over there for safekeeping. This resulted in a lot of system instability, and so that was one of the motivations of HanoiDB. It's like we needed, it never ended up hitting production React clusters. In fact, there's actually one. There's a storage engine created by Martin Sumner at the NHS in the UK that has a lot of similar characteristics to HanoiDB and to LevelDB. It's called LevelEd, and so he brought that into production for himself and his team at the NHS, but HanoiDB never made it into a production React cluster, as far as I know. Still, I think its design is really interesting, and especially that explicit notion of back pressure against writes, which you need for stability. You sacrifice throughput. Like, that was the thing that was really great about LevelDB, is the throughput was really, really good until it wasn't. But with HanoiDB, it's like, well, you sacrifice a little bit up front, but maybe overall your latency curve is less spiky. So anyway, with that, let's look into where we were last time, and we'll get started. Okay, so last time we were looking at we were creating this merger struct. Now we got all the warnings in here because this thing is not used yet, obviously. But we have an iterator over the A file and the B file. And note that these have the lifetime annotation here that we needed for the tree entry iterator, because it's borrowing from the tree struct. And we wrapped peekable around it. Now we could have done this with like Boxstein. I just don't think it's necessary, because we know that we want to be able to peek. And then and then we're iterating over every entry in a tree. And then we have the output file. So this is the X file I mentioned. This is the writer. So we have a writer. Remember, we defined the writer over here. It's just like, to construct it, you give it a path. And so when we are creating a merger, we will probably go, here's a path, here's the level that we need to merge. And it'll take the A and the B files and construct an X file writer, and then we'll trigger it with, do this many merges or something. So we implemented one step. And I think it's good to go over this again. Remember that we need to not only merge the two files, so this is like, this is merge them in like a zipper merge in traffic. One car after the other, each going alternating. It's not really alternating, because the key in one may be, there may be more keys of a lower lexical ordering than in the other one. There may be a slew of them in sequence, and then it switches to the other one. But essentially, we are going to take, so we're peeking on each of these files that we're iterating over, and if they were at the end, then we did no work, and we can just return. If there's nothing in B and there's something in A, we add A to the X file, and we return that we merged one key. And then here, if there's nothing in the A file, but there's something in the B file, then we take the B file and we say we merged one key. Now, if both of these iterators, so let's say we're in the middle or toward the beginning of the merge, both of these iterators will have something to consume. So we need to look at whether the A key is less than the B key. Like, how do they compare? So if there's a so we compare those two. Now this is a reference to an entry, because we're using peak rather than next. So if A is less than B, then we consume from the A iterator and we return 1 as the count. If they're equal, we know that based on the structure of the files, the A file was written before the B file. And so the B file is newer, which means we need to discard the key from A, and we need to return, like we need to merge the key from B. It's got to be newer. And since we consume 2 keys here, we return 2 as the count. And then obviously if it's greater, then that's the inverse of A. So we take B and we return 1. And then we add that entry to the file. And since add takes a result or returns a result, we want to return that count. You notice we're doing add.entry.map on all of these. So if the add method returns an error, then obviously we didn't merge it, and so we can't count that as work done. Now that does potentially invalidate our merger, so we'll have to think about how we handle that. And maybe we'll do some error handling at a higher level, but this is essentially do one step in the merge. So we can go up a level from that, and we're gonna have to look back at the Erlang code again today. I hopefully won't spend too much time explaining it since we did that last time. But we're able to, we should go up a level and go, hey, we need to do this many steps. And so we'll go through, maybe we'll do a while loop and keeping track of the count of how many steps we've done, something like that. Cool. So let's take a look back at the Erlang code, so we can do our orienting around what we need to do. And there was so in this case, the merger was a PID, was like a separate process. This is in the level. The merger on the Erlang side is separate lightweight process. So we're going to have to deal with the fact that this is, a lot of stuff related to handling messages from other processes, and it's kind of intertwined with doing the merge work. So that's one thing that we're going to have to untease to get the Rust code to do the correct thing. And yeah. Okay. So we have the merger, and I think that in some senses this is just doing this stuff, right? So like there was this scan function, which was related to comparing the keys. And this was interestingly, this is getting them in chunks. So it's populating. Yeah, it's getting a chunk of the file at a time, or a block is what we've called it on the Rest side. Right, and there's so this this step message is being sent from the level process. That's what's in this receive block. So we probably need to go, and I'm sorry, there was a receive scan. Yeah. So this is saying how many should we do, and this n is being tracked in the merger of how much work we did, and this receive step how many is adding that So whatever work it has going on currently, it's adding that, say here's more work to do. So, and go to definition, still doesn't work. Okay. Right, so so it stops merging when n is less than 1. And there's this step function which we implemented in the merge one. So that step function is just like, given this, add this, subtract this many steps. The from, again, is a PID. That's, if that's not obvious, that's the process ID that it's going to reply to when it's done. So I think we have a lot of what we need here. I think then what we need to do is in our merger, we need a something like the work to be done that was computed here. So like when it's down here and it says, it sends this work to do here to the merge PID. This is the thing we need to keep track of. It's like that n in the process state in the merger. So let's for lack of a better word, let's just call it n. And I think the essence of this is going to be, let's call it incremental merge. And this is going to take mute self. And the work is going to be a usize, and this is going to be a result, right? So I don't think that we need to here care about what level we're at. We do need to make a constructor for this at some point that will take what level we're at and open these files, and especially that one. And maybe n is not the best. I mean, it's what it is in this code. So what we'll do here is we'll say self.n plus equals work. The challenge here, I think, will be there's also a possibility that this should maybe be an I size, because I think that, or maybe we use like an I64 or something like that, because this could go below 0 if we like got to one of these steps. So for example, let's say n was 1 and we got to this step and a and b are equal, and so we did 2 keys and now we have -1. You know what, let's do usize. Let's keep it usize, and I think that what we'll do is when we do a merge step, we'll do saturating subtract. So if you're not familiar with that, all of the built-in types that can potentially overflow or underflow have these. Well, they have checked methods, but they also have what are called wrapping and saturating methods. So you can decide. You don't just do subtract or add or multiply or divide or whatever. You can decide what happens when you overflow or underflow. This is really important for safety, so you don't get stuff like, you just subtracted enough from a usize to make it underflow, and now it's at max. So we can do saturating sub on the result, and then in this example you say, so if it's 13 and you subtract 127, you get 0, rather than getting some super large number because it's underflowed. So that's what we're going to use, I think. Okay, so then we can say while self.n is greater than 0, and we'll say okay. We need to return okay regardless. So we will do let step is self.merge step ? So that's going to return a usize, and then we'll say self.n we do saturating yeah, let's self.n self.n saturating sub step. Okay, so now that was like way easier than I thought. We need to handle the case where there's nothing left to do, I think. And maybe what we have here is we have a return type that's not unit, but is something like we can close this. I think we should have a look at what happens over here. So let's look at the scan. Okay, so this one is if the keys are non-empty. Right. Okay. So if we run out of work and there's still keys to be read from the file, then it just goes back to the receive loop. Read from either file. Right. So this is kind of a little bit of a state machine. If you run out of one of these, you switch to this scan only version. Now what we've done is we built that into here, where it'll just if the other one is empty, it'll just use the file that still had stuff in it. So this design is slightly different. And again, here it's kind of implementing the same thing, but being in this, I have only one file. Okay, so when it's down to only one file, if it runs out of data, so end of data, it'll close and terminate. So I think that what we need to do here is look at writer. So we designed this explicitly such that when you close the writer, it consumes it. And I don't know if we have, with the way we put this together, now, okay, so what we could do here is have, I think this is the crux of it. What we should do here is make this consume potentially, and this will be a result of option self. So if we get here, we return okay self. Okay sum self. And I think that if we get to this, if this step I'm trying to think about the semantics of this versus borrowing. Because if we borrow, okay, I want to invalidate this merger when it's complete, right? So if we run out of stuff in the file, in the both of the files that we're reading from, you should not be able to use this merger anymore. Which makes me think that this should be a move, right? Remember, this mute here is just a pattern match. It's not like this still consumes the thing. But that means if it's not done, we need to return it somehow, right? This might make a little bit of an awkward API, but I think it's the right decision to make. So what we're going to do here is if step is 0, then we need to do self.writer, self.x, close. That'll consume it. And then we do okay, none. And then this thing is gone, right? Like it's consumed by this method. Yeah. Okay, let's see what the compiler says. We need to return. That helps. Okay. Again, this close returns result. So we need to make sure that we've got that handled correctly. Okay, so I could actually combine these two. Rather than that, we can say return self.writer.close map, and we don't care about it because it's unit, we return none. Self.x. Okay, so if we cannot remember this merge step, like if there's nothing left in either of these files, we're done. There's nothing more to do, and we should close that file and move on. Now, I think that there's more stuff going on. Well, no, it just terminates. So I think that what we need to look at is what happens when the level receives this step done message. Because I think that the interesting thing here is it will also receive a down message because this merge process is monitored by the level. If you're not familiar with this, I'm sorry we keep jumping between paradigms here, but it's essential to understand. So over here, so it's monitoring the merge PID, right? And it's saying, it calls, send this message step. This is the from, self and monitor and how much work to do. If we go to the main loop, probably. Right, so if we go to the main loop, we should see something with a down message. Okay, so we're again here in this dispatch over the okay, so if we get a step done, it stops monitoring that merge process. Now if it gets it down, that actually means it died, right? So the order here is explicit, and you want to handle step done before you handle down. That makes sense. So what is not clear to me So it's still going to, no, it demonitors and it flushes. So it's not going to get this message if it's already handled this one. So this demonitor with the flush argument says scan my mailbox and remove any down messages from this monitor reference. So it's never going to hit this case. Okay. I think we need to look at this reply step OK again. We've looked at it probably half dozen times, but yeah, okay, so it's just replying if it has somebody waiting on it. What I was wanting to see was the equivalent of what we have in the nursery, which is when you write a file and you close it, it gets injected into the next level. And I think that we need to look. There's probably here in the main loop. Where did that go? Main loop. Inject. Right. So this is receiving a file from a lower level. I say a lower level. It's a higher level. It's a shallower level. It's a smaller level. And this is just deciding how to name the file. Okay, and then it's opening readers for this. So okay, and if the set position is state B, then it creates a merger process. So set position is just like records in Erlang. They are not structs. They're like tuples, where the first element of the tuple is the name of the record as an atom. And so you can treat, this hash state.b is replaced by the compiler with an index into that tuple of what slot in that tuple is the B named field. So that's all done at compile time. So it's more like a I don't know what else to compare it to, but it would be like doing a tuple .1 or .2 in Rust. Anyway, so that's really just saying here, like, we need to know which slot in our state record to replace. That's what this set pause is. It's like, hey, if there's no A file and there's no B file in this level, then make it the A file. If there's an A file but no B file, make it the B file. If there's both an A and B, so we've already got a merge going on, make it the C file. Okay. So, excuse me. What I don't see here, and we're going to search this. Yeah, what's interesting here is that I think this process will crash if we lost our spot. This process will crash if there's already a C file and you're trying to inject one. So the math better work out. Okay. All right. So over here, I think our incremental merge, gosh, that was like way simpler than I expected. The trick here, I think the curveball we got was that um, we need to consume this writer if we have no more work to do. So making this method consume the merger and potentially destroy it was the interesting part. So we need to start thinking about what a level looks like. Um, and so maybe let's do that, and that can while we're here, let's go ahead and make a um, and we're gonna say this is going to be there's gonna be a path impl as ref path and then the level is going to be usize, I guess, doesn't matter. And this is going to be a result to self. So maybe this doesn't. That's actually interesting. Maybe this doesn't take these arguments, because I think that what we need to do is we need to create a level struct, and we'll just pretend that that exists. We'll create that next, right? So we need to do self. And we'll just leave this as to-dos for now. I think this is pretty easy to do. What we're going to need to do here is get the path, and maybe we go ahead and take that as an argument. Path. And the level is actually the thing that holds the A and the B trees. The other option is that we create these when we create the merger. That's probably the better idea. Yeah. The problem I'm running into here conceptually is that first of all, I hate this number of arguments. But we need to construct a path name which includes the level. So let's see, let's X file is path as ref to path buff. And then we join. We're going to format. And this is going to be X level. And what were they, dot data? Yeah. And does join return a result? No, it just works. Okay. So then we need, so this is just A, right? This is just B. And here we need to do writer new, and we'll pass it X file. And that needs a question mark. Okay. Let's pull that out. Okay, so I think we have enough to be able to call this from the level. Because this merger doesn't need to care about which file is which. It just needs to know what order they should be considered in, right? So I think that what we'll do is we will we could even have it do take tree entry iterator and call peak on it. I don't know if that matters. Okay. So that needs to be pub crate. This can remain private. So what we should get here is if, level is 10, this will be x-10. If level is 11, it'll be x-11.data. And then the level, when it calls incremental merge, so we'll be creating a level struct here in a minute. When it calls incremental merge on the merger, it'll potentially return the merger saying, hey, it can still do more work, or it'll return none, in which case it's closed and we can inject it into the next level. Okay, so we're not using that. And we don't need IO write or file options. Let's just clean up our imports here. Okay, so I think this needs, just for safety's sake, derived debug. Yeah, that doesn't implement debug. Fine, no debug. We don't need clone on it or anything like that. Maybe it just doesn't need any derives there. We could implement debug ourselves. Like, for example, if this writer has something... That might be actually interesting to implement debug for writer, so that we could say, hey, what file is it, and how many keys are in it. Let's take a brief diversion. Writer. Okay, so in here, this is a formatter, so we can say f.debug struct, and it's going to be writer. And then from there we can do field, and let's say file. And I don't know if we can get from a file struct what file it's writing to. That is, okay, that's experimental. That's experimental. Oof. Okay. It may not be possible. We may need to keep track of what the file name is. Oh wait, it's index file, derp. No wait, but that's a... Yeah, that's the actual file. I think we didn't keep the file name. So the other thing that I actually got wrong here is we don't need, well, no, we've got the path. So if we're just joining X level data with it, that's fine. Let's add that. I don't know if that's going to work. Nope. Okay. Yeah, so let's just make it a path buff. To path buff. We just did that. Okay, so now we can go. Let's fix that. Import that. Thank you. So now in our debug, we can say so field. What does field take? Right, it takes something that implements debug. So does path, you know, obviously things that implement display implement debug, but let's look at path buff. It implements debug, so it's fine. So we can say self.name. Can borrow it. And we want to get, let's say field count, and we'll say self.count. And now we've actually used that method. Finish. Is that it? Okay. So that will let us debug the writer. That was a little bit of a diversion there, but what we can do here is we can now implement debug for merger, and we're gonna have to put the, we don't actually care what the lifetime is in this case. We have to name it though, I think. Okay. And let's do f.debug struct. Merger. Field. And we'll say let's say writer, and we'll give it self.x, and then we're going to have field, let's say pending work, I guess. I don't know what's a good, maybe we can just say n, because that's what it's called. N, and then we will say self.n. Finish. If you've ever implemented inspect in Elixir, this is not that different. That you kind of have an algebra for constructing the output. So debug has that with this debug struct. You can do debug tuple, you can do debug, let's see what else is on that. I think there's like debug sequence. Yeah, so you can control padding, you know, you can debug a list or a set or a map and so forth. So you can create more semantic things rather than worrying so much about the contents of the output itself. Okay. You were saying that is unused. Yeah, well, because nothing's calling incremental merge. Okay, so now we've got debug on merger and writer. And I think now it's time to make, oops. Now it's time to make the level. And then we can go up one level and go what, up one level, and go what is the structure of the thing that contains the levels. So let's make sure that this is part of our code tree. Okay, and we're going to use create merger star. Okay, and I'm not sure what's going to need to be in here yet. But here's what I suspect. We have A, which is going to be an option. So use create format star. We'll just start with that. We don't know if we need all of that. It's going to be tree, right? And the same for B. And the same for C. And then we're going to have a merger. Sadly, this is going to require us to have a lifetime variable there. So I really didn't want to do that, but because this merger is potentially borrowing from these things, it also feels kind of weird to have all of these things be optional. So we're gonna have to think about what we need to do in here. Let's look at the Erlang code again for a minute, because I think that we are also going to need level, which is going to be usize, right? So that we can create this merger. And there's also going to have to be a path in here, which is a path buff. So that's going to be where does the level live? And maybe we go ahead and make the new function here, which is going to have a as ref path and level. It's going to use size. And what we should do is for each of these we will be checking whether these files exist and potentially constructing the merger. And this should be like, this should be result of self. Okay. So It's starting to come. I'm sorry if I like froze there for a second. It's starting to come into like formation in my mind a little bit. Again, I really don't like this lifetime annotation here, especially when it refers to a lifetime that comes out of these. But I don't think it's going to cause us any trouble. Now, what we could do potentially is see if there's a way to do this without the lifetime annotation and make this merger convert its references into static, but interestingly, that might not be a bad idea. But we potentially have some problems there if we have multiple things going on and like the file handle, like the position within the file jumps around in unpredictable ways. We may run into trouble. That's something I hadn't thought of yet, but we'll need to contend with potentially. We'll need to look at how this yeah, I think this tree entry iterator, right, so it uses the entry iterators. Over the blocks, yeah. So, interestingly, we're going to have to look at this entry iterator. I think it just uses positions, which is fine. It just expects the file handle to be exclusive to itself. So as long as that entry read function, sorry. So this entry iterator, right? Okay, so it seeks the file to the spot where it wants to read next. So I think that we're fine on that. There's some potential thrashing there if we're not careful. Looking up random keys. Meanwhile, there's an open entry iterator that might need to seek it back to a different spot. Yeah. Okay, one second. Let me turn the fan on. Okay, so I actually don't think that that's a problem. I was concerned about this expecting that all of our reads are going to be sequential through each block. But if we've got, this merger going on and it's using the tree entry iterator, which has, that has a stack of entry iterators over blocks, right? Because it's iterating over each of the depths of the tree, like each of the inner nodes and then the leaf node, in kind of a stack. I think it's going to be fine. Simply, it's going to be fine because that entry iterator seeks. Like if I had done that differently, we might have had a problem. But I think we'll be okay. Okay, so let's do this the dumb way first. So we're gonna do let path is path dot asref to path buff. So this will go into our struct. And then we're going to go if we need to do something like file exists. Right, so path, right. And I think I shouldn't have moved that down. Path buff, if you so deref a path returns a path buff. So this creates a new one. That's fine. If we don't want to, so the join method there creates a new one. If we don't want to do that and we want to modify the current one, we use push or pop. Okay, so and we're going to say format a level dot data, and I think that that's going to probably borrow that. Exists. So this is going to return a path buff, and maybe we do, let's say a file is going to be this. Then we're going to say, actually just do let a. So if exists returns a Boolean, and then what we'll do is we will want to open a tree on that. So from file. And then, so this is where it's getting a little tricky. So a, here, save and then tell me what that is. It doesn't know what that is. This is a path buff, bozo. How do you not know that? Here, let's just say and we're gonna have to put to-dos on each of these. So okay, so A is an option tree. So what I was, then is actually what I want. How did it know and then? There's no way that that actually works. Okay. Okay, so this should be like option result tree. So what I want is to transpose and question mark there. Because if we can't open the file, we need to return that error. But what we want is an option of a tree. So now we've got option tree. And yeah, so transpose returns, converts a result of an option into, or an option of a result into a result of an option. You can do the same also of options of results. You can, or results of options, you can flip them. Okay. So then we're going to do the same. Let's just copy pasta this for B. We'll say B file, B, right? And we'll do the same for C. And this needs to be B file, and this needs to be C file. Okay, so now we've got those. Now we need to decide if we're going to create a merger. So here we will do if A is sum and B is sum, then we'll need to create a merger. Maybe we'll do it like this sort of thing. Maybe let's do match A and B. I'm going to say let merger is this. So if they both exist, sum A tree, sum B tree. And I think that what we need to do is borrow here. Ref. I don't know that that's strictly necessary, but we're gonna put those in there because I want to make sure that I don't consume those in this match. So if there's some, then we need to create a merger. Otherwise, if either of them are none, then we just return none. The other thing we could do is go A zip B and map. This is fine for now. Okay, so if they both exist, then we need to create this merger, right? And it takes the path, the level, and the iterators. So we need to say sum merger new. Okay, and that's going to take path. We'll borrow path so we don't consume it. And it's going to take level. That's copy, so we don't need to borrow it. And then it's going to take a tree dot entries peekable and B tree entries peekable. Okay. Oh, and we need to put question mark on that, right? Entries is a result of a tree entry iterator. Cannot infer type parameter T on declared enum option. I wonder if I can I'm gonna see, because I think there's some weird borrowing thing going on here. By the way, as ref is your friend on option, it turns a borrow of an option into an option of a borrow, and then I can remove these refs. Not that that's a big deal, but that solved it. Okay, there was some ambiguity there. Okay, so really quickly, let's talk this through. So if the A file exists and the B file exists, we need a merger file. And one thing that that the merger probably needs to do as well is assert that this existing file does not exist. So if we got into a crash state and the X file is there, it needs to delete it. And I think that that's what it does on the Erlang side as well. Because we don't know what state that file is in, if it's corrupt or not. So start. Okay. Interesting, it's called C here. In this one, it's called X up here. Oops. That was probably an oversight. I think it might actually be here in the writer that if that file exists, it just crashes. Let's look at that do open real quick. I want to say we've handled this before. The thing is, it does raw append. Okay, on recovery, the X files are deleted in recovery. Okay, so probably what we need to do is when we're creating the level. Thank you, Greg. Also, hi. Thanks for coming. So when we're creating the level, we need to assert that this X file does not exist, and just delete it if it does. Because I'm pretty sure that now it may not actually matter. There's create new. Yeah, so this will fail if it already exists, what we've done over here in the writer, which makes sense because that's what we wanted on like nursery data and so forth. But we need to make sure that when the level starts up, if the X file exists, that it doesn't. Yeah, there's a question here in my mind of whether. Sorry, I'm gonna merge imports. There's a question in my mind whether this should delete that file on startup. And I think the answer is yes. Just a question of, is it in the level? Or is it... Okay, now we're getting somewhere. Is it in the level or is it in the... is it in the merger? Not sure what the answer is yet, but let's see if we can fix these. Yeah, A does not live long enough. Okay, we're just going to do... Let's put this back the way we had it. The other thing we can do here is just say we don't care what the lifetime is. Otherwise, we might have to use a universal quantifier, and I kind of don't want to do that. And then it's assumed to be the same missing lifetime specifier. Yeah. Can we fake it? Can we go static? Will that work? Yeah, this is not borrow for static. Damn. Got foiled by the borrow checker. So now there's a possibility here that what we could do instead of this, I want to say that we made tree clone. If we did, then we can clone it. That will mean that we need to make the merger own those two things after they're cloned. But let's look at, we did not make it clone, but it only contains a file handle and a U64. If we can clone the file handle, if it's safe to clone that, it does not implement clone. I guess that makes sense. Okay, interesting. No buffering. We may need to handle that at some point. That we are not handling that right now. So there's a try clone. Interesting. So it has a fallible clone, basically. Okay, so let's look at level again. We could say, yeah, let's do that. Let's make a method on tree called tryclone. Which will be basically like and then we'll do okay self this is file, or no, it's tree. Okay, no, it's file. Why did I think it was tree? Gosh. Okay, and then we do file and then len. Actually, we'll do this will be self from file. Is it not? Nah. Okay. Well, we'll do len equals file dot metadata dot question mark dot len, and then we'll do okay self file len. Okay, so the reason I'm doing this is so that we don't have to muck with lifetimes, right? Yeah, that's a method. Oops. Because I think that while this is fine, what we really want in here is the tree in the merger, and because otherwise we're gonna get all this confusion about that. The main problem here is that this, as we have it, even with this lifetime annotation with tick a rather than tick static, is that this thing borrows from these. So it's kind of self-referential, and Rust doesn't like self-referential data structures because it can't prove things about how long something lives. But what we could do is clone each of these and pass it into the merger. And the merger can own the original trees as well as these iterators. And I mean, it's still self-referential, but the lifetime is on this, then not on this. Okay, so what I'm thinking about right now is if we go ahead with this, what we're going to run into is that we're going to do something like let new A, for example, A tree triclone, and we'll do let new B, B tree triclone. And then we're going to pass these into merger. So we're constructing let me take a step back and say we're probably doing too much here in this constructor. Maybe what I want to do is go let level we'll do something like this. Because there's also a point at which we'll need to create a merger if somebody injected a B file into our level, right? So maybe this is created at that time. So maybe we do, we have a method that's like maybe create merger. And then, okay, level. And then we'll just say for now it doesn't do anything. But we're going to need to be able to create that. And maybe what we'll do then is we'll handle the lifetime crap down here. Ah! Okay. So it's not self, but level. Okay. Okay, so here's where we would create the merger. Again, the issue that we're going to have to deal with is that this basically has to own the tree. So we're going to have to go ahead and make that refactor. It feels a bit janky. The thing is that this is going to be used for reads from multiple places regardless. So we kind of need to have copies of the file handle. I want to look in here real quick. Right, so okay. Yeah. All right. So our supposition here about what was going to be in this was slightly wrong. B tree, haha. Okay. So what we need to do here is this needs to be a tree. And let's rename this. And this needs to be a tree. And then what we'll do is we'll do a tree is a dot entries dot peekable. Not a tree, let a. Got that switched. Now, I don't know if it's going to like this, because I think that it's like... Yeah. We're basically running into the same problem. And then you can't have one field that borrows from another. One field in the same struct. Now we could do something like... we don't care what the lifetime is. I don't know that that's going to change anything. Probably not. Yeah. Binding a tree. Okay. So yeah, now it just doesn't have a name. This comes down to like our design being slightly wrong. It's something that we didn't account for earlier. Like, even though we can do this, you know, try clone and so forth, this tree entry iterator borrowing from now that is another option. We could make this not borrow the tree. We could make it clone. And maybe that would solve, you know, we would do the try clone. And that would solve this lifetime issue. And I think maybe that's the answer. Yeah, because like we already had to do this try clone, right? So why don't we do um, we can either try clone here with the question mark, or we can try clone inside new. And I think that let's do it explicitly here. And this will be no lifetime. And let's get rid of those lifetimes. But then we're going to have the problem of this borrowing. Boo. That only solves part of the problem. Now this one worked because this is a borrow. Interesting. What if... This gave me an aha moment. Let's put this back to self like we had before. So over here in the merger, what if rather than this, this takes tick A, and we need to put the lifetime annotation back in here. And this takes tick A tree. And then we don't have this. Okay, so this is fine. Now up in level, I think as long as we've got this in there, let's see if we can do this. This is probably not going to work. Self.path. Self.level. A tree, B tree. Interesting. So what's the error here? Oh, I need the... It probably is going to show me once I've got these annotations on there. Okay, so this needs a question mark. Lifetime may not live long enough. Yeah, and I think it's that tick 1 must outlive tick A. And I think it's that this borrow, when we do this, that doesn't fix it, but it does narrow it. And again, we are getting into the requires that this is borrowed for the length of, yeah. I thought I had something there. Note that it was fine when we had both things borrowed. So like this was already a reference, and then that lifetime extended to what's in these entry iterators so that they have the same lifetime. So we know that even if this borrows from this, that it's going to live at least as long as that, right? That's what that lifetime annotation means there. So the problem... Now, maybe we can solve this. maybe we can say this is tick A mute self. Aha. So now what we've said is this borrow lives at least as long as the thing that it contains. Now we've moved the problem up here. And because what I want to do is I want to associate this lifetime here with the lifetime of these things. I mean, I could do static and lie, and that probably still doesn't solve it. No. Right. Cannot move out a level because it's borrowed, right? Because it's like, it's immutably borrowed. And hi, Isaac. Nice to see you. It's both mutably and immutably borrowed in this context. It feels like what I need to do is push this problem up another layer such that this is like, these are like option tick A, like so. The problem will be then, now this level's not really responsible for its contents, and that kind of bugs me. In which case, what we would need to do is like pass these in as arguments, right? Okay, we're gonna forget this for a second. The problem is this is now an invalid state. Okay, thank you, Clippy. I don't need the borrow. Okay. Yeah. Now it's like, this doesn't call. This is never called. The other thing is that as soon as, so remember, we put this tick A in here to assert that this mutable reference will always live as long as the container. Now, what we could do is say this. And this will be result self. Yeah, now we got those same problems all over again. Okay. Yeah, that doesn't solve it. I think this is a case where I'm going to have to read up on how to handle this sort of situation, because we've got an issue of we need to initialize this, and this merger struct, regardless of how we put it together, has references to a tree. And either the self-referential thing is down here or it's in a higher level. And in order for it to work correctly at the higher level, we need to create something that contains a reference. And if this owns those trees, then it cannot contain this. And I can get rid of this static annotation. Now there's a possibility here that maybe I need a universal quantification on this lifetime or something, but I don't know. I don't know if that would solve anything. But there's also the possibility that what we do is this is not owned by the level. We have, like, in the database, so to speak, like this merger does not exist, but we have like a pair of level and option merger, and then I think we'll still have that same issue. If we tell this merger to do some work, like if we create the merger and stuff it into the, the tuple, it doesn't know that the lifetime of these borrows will, like, I don't think that it can prove that that lifetime is long enough. Now we could let's maybe think about that, and rather than mute self, we do tick a self, and let's like forget that the merger should be part of this struct. Let's make it not part of this struct. And let's help a little bit here, inline that variable. Okay, so yeah, and then now this is not, what I'm going for here is can we make okay, so now what we've created is you can start a merger, but it's not owned by this level. And again, I can remove this lifetime annotation because it's not generic over that. What's wrong? Oh, it's just not called. Okay. Now the merger has to live outside. The question in my mind is, because this merger is going to be long-lived, can we create a data structure which ensures that that merger lives as long as the level? And I think what we can do is something like this is not, we're not going to keep this code around. I just want to demonstrate what I'm thinking. We'll call it level wrapper. And it's going to be, level is going to be tick A of level, right? And then merger is going to be option merger tick A. And then that means that maybe we'll keep this, I don't know. That means that we can assert that this, first of all, we're borrowing the level. This seems kind of silly, in fact, but like we're borrowing the level. I think we're still going to have, like, whatever holds these things is still going to have a problem of, well, you've got to borrow this for as long as this thing lives, and you know this thing has to live as long as this. And what if you own these things? Now you've got this lifetime annotation that has to line up with the things that you own, and and so, like, maybe we need to rethink the structure entirely. So what I was trying to go for is, like, this kind of looks like that tree entry iterator, or the entry iterator, right? Like, it borrows the thing that it's consuming, and then it has something else that has a related lifetime. But at some layer, we have to have something that owns. And I feel like it's gonna look like something that has a B tree map of like a usize to a level wrapper, or a level, or something like that. And it's gonna have a nursery, which is a nursery. This is not production code. We're going to toss this, right? This is not code we're going to keep. But it's going to look something like that. And there's no way unless we pop it all the way out to the top level to where it borrows from this, essentially. I think there's no way to ensure that these lifetimes that are vexing us are going to live long enough. Because they need to live at least as long as this. Because they need to live at least as long as this. And they're not temporary. They are long-lived. And as long as this has, you know, what we care about in this merge step is iterating over that file. And we want to keep that iterator is around as long as we need to be able to do incremental work. And we don't want to recreate it on every step, because that's just pointless. Now, another thing I considered is that maybe we make yeah, maybe we make cloned versions of these. Like maybe we make owned entry iterator and owned tree iterator. Maybe that's the only solution that we can do. It does mean that this is no longer generic. um, the other thing that's interesting about that is we have this returns entries. So, you know, the entry read returns own entries. It doesn't return borrows from the file. And that was necessary for other reasons. So I wonder if it's not too much of an imposition to make these owned. And they do triclone. Okay. You know, I'm willing to go over. Oh, hi, hi! Welcome to the stream, Manoj. I didn't see your message a few minutes ago. What Hanoi aims to do. So, Manoj, HanoiDB is a LSM tree style data store, so key value store. It is ordered. The contents of its files are B trees. So you can do stuff like iterate over all the keys in order, or use it to store secondary indexes on some other data. And being an LSM tree, it has good characteristics for high write scenarios. In that, you know, the storage is tiered. It's not a single B tree file. It's multiple B tree files that are layered and log structured, meaning that like the things that are they're written to in the order they're received. So please do, yeah. If you want to know more, look up LSM trees as the paper. You can look at the original HanoiDB repo that we've got open here. This is it. It's originally in Erlang. Okay, so Isaac, coming in a bit cold, but why does the merger need to be stateful? The merger has to be stateful because it's not going to merge a file all in one go. It's going to merge a certain amount of work at a time. And then, you know, of course, when it reaches the end of the file, then it's gonna, you know, close and consume itself. So the idea is not that, well, so if it, in a very naive setup, we're not going to do it this way because that's not how the original HanoiDB did it either. In a very naive setup, every key you write would trigger one step of merge work on every level so that you never overwhelm. But it's more like, well, we go up to, say, 256 keys, and then we trigger 256 steps of merge work on the top level, and then it multiplies, you know, so that it scales with the depth of the tree. It multiplies as you go down further levels. So that's why the merger needs to be stateful. It's that it's not going to do all of its work at once. It's going to do it a little bit at a time. Okay. So I'm going to, we're basically going to redo this. I'm going to make a owned entry iterator. And we're going to do the same for a tree entry iterator. And this is going to be a file. It's going to be a file, so we're going to own the file. And this feels like a little bit of silly duplication, but I don't really know any other way to handle this. And then every time we need to make one of these, we have to clone the file handle. So that's going to be a potential issue with and that'll borrow that. Okay, so now we have an own entry iterator which has the file handle. Like, it's not borrowing the file handle, but we're gonna have to do try clone on that whenever we create one. And let's do the same with tree entry iterator. So we've got this one, and we're gonna, let's owned tree entry iterator. And then, like, if we can eliminate the lifetimes, then like this will make our lives so much easier. There's gonna be a potential issue here with, we're gonna have to clone this tree to get an owned entry iterator. Sorry, not tree entry iterator. It can't be self-referential that way. I really should rename that. Okay, then we're gonna have to do something like this as well. And this, we need to remove the lifetimes. So root block, and we're gonna say owned entries. And we'll make this, or entries owned is probably the better way. And this is owned tree entry iterator. Oh, for Pete's sake. Okay. So we're going to have to make that method. And then we're also going to have to do this for this iterator, owned tree entry iterator. And then here it's going to be entries owned. Now we are going to have to define this, and I think the problem here is potentially that we're going to have to introduce a panic, or we're going to have to introduce a result, and I think that maybe we do result. Yeah, let's do that. Okay, so the logic is essentially the same, but we're making this entries owned method. So let's go up and make that. And this will be like we do try clone in there, right? Okay, so we've got entries, and this is, I'm sorry, this needs a tick, whatever. Uh-oh, what did I break? Oh, it needs a bracket. Okay. So entries owned. And this is going to return a result of owned tree entry iterator. No, yeah, on tree. That's correct. And then on block, we're going to have to make the owned entry iterator. So this is the owned tree entry iterator. New self.tryClone, question mark. Okay. So then let's go down to block. Where is block? Okay, so here's entries. What we want is entries owned. And this is going to be result owned entry iterator. And this is going to be try clone. And we need to do okay. We could inline this and say, yeah, let's do that. Map file, and then we can put that in there. It's, you know, I think in every actually we can't do that. I was going to say, otherwise we have to do like map error. Yeah, I was going to say there's. I was about to say something about Rust style. You know, the workplace that I'm at currently tends to prefer more things with if let or match rather than trying to pass map or map error. But it's kind of contextual. So, you know, try to find your own style when you go through this. This one actually kind of forces me into this specifically because the this IO result type is not the same as the result type that we've defined, because we have an error type which can be converted from a standard IO error. And so we need this question mark. This question mark implicitly does an into on the error branch. So so that's why we have we need to construct it this way. Okay, so now we have entries owned and entries. And okay, so now we have iterators which don't borrow, which was the root of our problem. And we're going to delete all this. This is just an example. And now I think what we can do is go over here in merger, and we're going to change this to an owned entry iterator. And then say bye-bye to lifetimes. Because we don't care. Okay, and then down here, we can say entries owned. And again, we don't need to worry about this. No lifetimes. Oops. I wish there were a code assist for that. No more lifetimes. Get rid of them. And yeah, let's put that. Let's put these above, because like if we can't read, there's no point in opening that file. Yeah, this should still consume. Yep. Yeah, fine. We need to fix it over here. So now we can say here. Let's see if it'll extract that into a variable. Yep. Okay. So now we can say level dot, and this is, we're going to assign. We're going to have this in here. Mergers option merger. And this will be we're not going to do this anymore. We're going to assign into the struct. And we'll say if self.merger.isSum. Return okay. Now the other thing we can do here is actually this none self.merger. We can do that. Remove the semicolon, that goes there. Okay, so how is that mismatched? What did I do wrong? Oh. The only reason I'm putting this in a and this needs to be mute self. The only reason I'm putting that in a separate function is that we'll probably want to call this like when we receive a new file. Okay. Wow. So yeah, like our original assumption about what a merger needed was wrong. I think that given the way that we're using these clone file handles, you remember this, if you go to this entry's own definition, it does this, and it takes a tree, and this try-clone calls try-clone on the file handle. So if the file is if we can clone the file handle, then we can basically create a new view into the tree. Now it uses the same file descriptor underneath, so like we need to make sure that in our code we're never expecting the pointer into the file to be at the same spot every time we try to read. We always have to seek. What is owned now? The tree, and that only has a file, so no memory is cloned. The question, okay, so what is owned now? So we have, and it makes more sense if you look at these structs, Isaac. So tree entry iterator has a lifetime on it, a generic lifetime, and that lifetime annotates how long the borrow of this tree lives, and then also the lifetime of the file that's inside this entry iterator. So if we go to that definition, we know that this borrow here has this lifetime. So these can line up. We know that they all live long enough. This is just helping the compiler, right? This is not about, it's helping prove to the compiler that our stuff is safe. It's not about, can you read from different spots of the file? So having the owned version means that this is not a reference, this file in here. And the same with the tree entry iterator that the tree is owned. And what I mean by owned is like from a memory management perspective, it's contained in that struct. It's not a reference. It's not a reference to something that lives over there. And I think that what we were running into when we were trying to have the merger struct have a lifetime on it, and the reason it would have to have a lifetime is that these iterators needed a lifetime. It was like, okay, well, how do you prove to the compiler that the lifetime of whatever this contains lives long enough? And we couldn't do it. So it's essentially the thing is this file triclone is cheap. So you can see here it's got this inner, which is like the operating system specific implementation, and it's just like, can you duplicate this? Can you duplicate this file handle? So we could look at whatever that inner is, and I think it might get a bit too dicey. See, it's got this fsimp. Can you show me the files? Yeah, so this fsimp is the operating system specific implementation of file. We're going to have to go read the Rust source to really understand that bit. I'm assuming that that's a module that's defined locally, or this might be a crate. This might be a crate. We really can't know. Other than the Rust, the standard library has this type. I'm assuming that, say on a Unix style system, so anything implements POSIX, this is like, that file descriptor is a number. And as long as that file is opened by the same process, and that file is not closed, then that number is valid. There's some concerns there potentially. And I don't know, like this triclone, it does duplicate. So whatever that method is in fsimp, yeah, let's go look at the source just for fun. Rust lang Rust. Yeah, but the tree never has parts of the data cache, so cloning a tree doesn't clone memory. Correct. All you're cloning here is the file descriptor, basically. Let's see. Is it in library? Standard. Yeah, so fs, oh, that's just test. Let's see. Yeah, the thing is, like, standard is... I wonder if there's some of it in core. Nope. I think that there's a thing here where we need to look at the operating system and architecture specific implementations. I forget if that's in like Rust standard or something like that. Or is it Arch? Let's look actually here. Is there an Arch? Yeah, standard Arch. Here we go. This is actually different. we might be going down a rabbit hole here. Yeah, and I think that Isaac brings up a good point. Like, we're not doing any buffered reading or managing pages ourselves or anything like that yet. We're just going, okay, operating system, give me this sequence of bytes from this file. And that's what, in my mind, makes it like not safe in the prove it to the compiler sense, but safe in the we're not going to violate any expectations of sequentiality of reads, because we're always going to seek before we read. Now that seek may be a no-op from the operating system perspective if we're just iterating across all the entries in a single block. But you know, down deep, you know, we've got this owned entry iterator, owned tree entry iterator, which has owned entry iterators, and these just have a start and end for the current block that they're trying to scan. So, and it's always seek this file to the start. Yeah, so I think, like, in that sense, we're not trying to do anything complicated there. But we do have the possibility that somebody issues a write. You know, this is still single-threaded database, right? So somebody issues a write, that triggers a merge, which means this merger needs to know where to start from. And so its iterators are going to seek each of those files. That may, let's say you're reading from the database, you're iterating over a block or iterating over the tree, and you're scanning that, and the use case there is you're scanning something and you want to issue a write. You may be reading from a file that gets a write sent to the nursery, which triggers a merge, and that new file gets injected, and now we've got merge work to do across all the levels. And so we've got potentially multiple iterators over the same file at the same time. Yeah, and data access will be serial for most operations, right? But like, from a safety perspective, we're always seeking to the beginning of that position for any time we do a read. Yeah. Okay, so that was way more complicated than it should have been, but we've got I think we've got what we want out of this, and we've essentially got incremental merges on a single level. What we need to go up to next time is so let's look quickly back at the nursery. There is this bit, right? The nursery, and here's something where we can copy those, it's not a big deal. I was going to say the nursery needs to trigger an incremental merge. So this is logic that we haven't handled yet. And what it will mean is that this write, this add, may not return a unit. It may return like, do this many merge steps, like a potential command, which is like, no op, or maybe it's just option of how many steps to do. And at that point, then whatever is calling this goes, okay, I'm going to issue that to each of the levels in turn. And that will probably be the next step that we go to. We go up a layer. So we have a level, it's pretty basic. But then we go up a layer and we have a container that owns the levels by number and a nursery. And here we don't need nursery here. We're not using that. Okay, so we still we still haven't proven that this works. We've just been proving to the compiler that it's okay. And I feel like we're a bit out in the weeds here, and I'm not sure that this is going to work at all. But what we can start to do next time is, assuming I don't have any syntax errors here. Next time we can go up that layer, make the database struct, so to speak, contain a nursery, contain all the levels, do the initialization and any recovery steps, including deleting the incomplete merge file. And then maybe we can start trying some things out, like, create a script that just writes a bunch of data to it and see the merges happen. So that's sort of the step that I want to get to next. This is probably one of the longest series I've done, aside from the Bevy game dev stuff, which I think we did for like 16 sessions or something. But I think that this has been super interesting for me, and I know that we have a lot more to learn as far as how HanoiDB is put together and like what we can what we can do with it. So next time, we will go ahead and go up that layer and figure out what needs to be done next. So thank you so much for coming, and thank you for your excellent questions. Really good stuff. By the way, next week I will not be here. We'll do another session in 2 weeks. So don't expect next week. I've got a friend in town, and then I'll be spending time with him. So have a great Sunday, have a great weekend, and go enjoy the hopefully beautiful weather.